Alright, guy. Another multi-phase flow simulation in Ansys Fluent, and this time I would like to study the phenomenon which is called train slugging, and it's very common in oil and gas industry, and that is the accumulation of liquid in low area of a pipe. So imagine you have a horizontal transport line which both oil and gas is running through, and then you have a vertical riser, and then you have a low area at the bottom of that riser which is like a bended area, and then you have accumulation of liquid at the bottom due to gravity, and you will have gas at the top, and this train slugging which we are going to study here will occur. So I have created a geometry here. This is my pipeline. This is a transport line of a horizontal shape, and then I have a riser at the top. So if you look at the dimensions as well, if I go to measure, so basically the diameter of my pipe is like 10 centimeter. The length of my horizontal pipe is 50 centimeter, and the length of the vertical riser is like only 30 centimeter. I have created this very simple geometry in SpaceClaim, and I have meshed it inside Ansys Fluent, inside the workbench. And in the setup, I have used a double precision. So I just simply click on the solution in order to see the mesh as well and the geometry inside Ansys Fluent. So if you look at the mesh, so what I have done in the mesh is only I have added some like 5 or 6 layers close to the wall to have this inflation layers close to the wall boundary condition. So the first thing you need to do is to go to General. This is of course a transient simulation, because what I'm going to simulate is the mixture of water and air in the inlet. So this is my inlet. So I'll tell you what's the mixture of oil and the water and air when I come to boundary conditions. But this is of course a transient. You need to check on the gravity and put the value of gravitational acceleration at the y direction. So the model I have used for the multi-phase flow is volume of fluid here. The number of Eulerian phases are 2, and I have checked on the implicit body force as well. Regarding the material, I have air and water, as I said. So air is default value, and water I have taken it from the Fluent database as well. The primary phases and the secondary phases, you just go to setting up the physics and the phases here, and you just list through all. My primary phase, I have called it air, and I have picked air as the phase material, and my secondary phase is water. There is no such interaction here except the surface tension between the water and the air. There is no such like cavitation or mass transfer between two phases here in this simulation. So I'll just go to surface tension. So there are several models for surface tension. There is one like continuum surface force and continuum surface stress. I have picked up the default continuum surface force. And the surface tension between water and air, I have picked up the constant value of 0.072. And this value, you can find it in the internet. Just Google the surface tension between water and air. Regarding the model for the viscous, I have used K epsilon model and realizable and scalable wall function. Then what I need to change is, or what I need to take a look at is this cell zoom condition for air, which is air, and then for the water is water here as well, just to double check that everything is fine. And then I come to the boundary condition, and then for the inlet, if I double click on the inlet, I have this velocity magnitude of 0.6. So the inlet type is velocity inlet is the is the type of inlet of velocity inlet. So the velocity magnitude is 0.6 meter per second, and the turbulent intensity is just 5% with the turbulent viscosity ratio of 10. And for the air, this is my primary phase, so the air is fine. And then for the water, I have specified the volume fraction of 0.3. So this is basically at the inlet you have the mixture of water and air, and the volume fraction of water to the air is just 30%. And the outlet is just pressure outlet with the gauge pressure of 0. But in the boundary condition, what I have done is the operating boundary condition, and I have my operating pressure is like 1 bar, and the specified operating density is the density of the air. So make sure to check on this one as well. The solution I have not changed anything. These are defaults, but make sure that you don't change the transient formulation. Don't change it to second order implicit, because the volume of fraction model, this multi-phase flow model that we are using here, does not work with second order implicit. This is a limitation for the volume of fraction. And then what else I have done is initialization. I have first initialized it with hybrid initialization, and then I have patched the whole interior, this FFF surface, with the water with the volume fraction of 1. So basically the transport line and the riser is initially filled with water. Then in the calculation activities, I have auto-saved the results every time step, and I have created the solution data export. If I double click on that, you will see what type of data I'm exporting. So make sure to have this file type to CFD post compatible in order to have the results in the CFD post later. And I have exported this volume fraction of water, molecular viscosity, volume fraction of air, density of air, and the pressure and the velocities as well. And perhaps you would like to do the same thing here in the data file quantities as well, to make sure that things are being exported to CFD post or being stored to use it in the post-processing later on. I think the setup of the case is almost done, and then I have to run the calculation. This is actually a very sensitive problem, because you have a train of slugging and things like that, so you need a very small time step, not a very small tiny, but something in order of 0.005. And I have put the maximum iteration per time step to 100, and the number of time steps I have actually run for this simulation is 200, 300 to have this complete slug training phenomenon being captured during the time. So if I just run the case for one number of iteration or one number of time step, you will see how my residuals look like. So here is my scaled residuals for the continuity, velocity, and K and epsilon. So this simulation is done. Now let's take a look at the final result. I'll close this, then I'll go to results. What I have done here, or what I have shown here, is a contour plot of water volume fraction. So if I double click on the contour, you see that I have the volume fraction of water as a variable, and I have put the number of contours to 100. So if I click on the time step selector, so if I start from time 0, so you see that the whole pipe, the whole transport line and the riser is filled with water with the volume fraction of 1, and then as the time passes, the air, the mixture of water and air starts to penetrate inside the transport line, and you will see this train slugging phenomenon. So let's take a look at the video I have created. So it's very simple to make a video. I'm sure you know how to do it. In the time step selector tab, use this animate time step, and just save the movie. Check on the save movie and put it to 0, and just click on the play, and once the movie is being played inside CFD Post, the movie is also being saved on your desktop or wherever you have put your movie here. So let's take a look at the movie I have already created. So here is the problem. So you have the mixture of water and air coming from the inlet. So it takes at the beginning, it's quite stratified in the transport line with the few bubbles of water on the top, and but here in the low area point you see the accumulation of water. So the amount of water that are being so here is my low point, and then you can see that the bubble of the gas or the bubble of the air is being transported to the top, and the liquid is being accumulated at the bottom. But at the same time, the water is trying to push up the front of the slug, the train slug, through these narrow gaps between the gas and the liquid. So you see that the water is being pushed up, but the gas is not completely out of the riser, and it collapses as long as the density or the gravity is working downward. So you will see the collapse of the air at the top of the riser, and very chaotic and very turbulent flow in the riser you can see here. So this is a train slugging phenomenon which is not desired in oil and gas industry, and there are several mitigation steps you can take to avoid this train slugging, which I actually have a tutorial in Olga in my channel. You can go to my channel and look for the mitigation strategies to avoid train slugging. I hope you have enjoyed this video. I'll come with more tutorials later. Thank you very much. Have a good day. Bye.